All right. So, what I want to look at today, I told you we're kind of going quickly through a number of these first sections because a lot of this you've seen before. But like this stuff, there are things that are still kind of challenging to really understand well. Okay? Can you put that away?
It really helps me, quite honestly. And this is like how I do my math homework.
I understand that, but can you please put it away? All right, that's fine for homework, but wrong one. There we go. Just a glitch. All right. So what we're going to look at today, we're going to focus in on magnitude and some algebraic vector operations. Okay. Yesterday we talked about component vectors, which you see right here. Okay. We introduced the concept of component vectors, and we can look at it either in component form like this, or we can look at it in terms of our unit vectors I and j. All right, both of those are technically component form. And remember, there is also some alternative notation here. You're going to see me write this as V1, V2, okay? Or you may also see it written like this, okay? Depending on what context you're in, people will use different ones. All of them are valid. All of them would be acceptable on the exam. And in this class, as long as you're using a valid notation, that's fine with me, okay? So, as you can see, we're going to look at the next 3 sections here because, again, you have seen a lot of this before, but it bears practicing as we prepare to get to 3-dimensional vectors. Everything we're doing with 2 dimensions, we're going to then apply to 3 dimensions. So we want to make sure we really understand and have this stuff fresh in our minds before we move on, okay? Now, magnitude. We already mentioned that magnitude is the measurement portion or the scalar portion of the vector. Okay, a vector has both magnitude and direction. Alright, so if we're talking about a force vector, this would be the number of pounds or the number of newtons. If we're talking about a displacement vector, this would be the distance that's being traveled. If we're talking about a velocity vector, our magnitude would be the speed that we're going. Alright? Now, when we're talking about component vectors, say when we have a vector 5, -3, or we could write that as 5i, well, I could use minus 3j. Both of those give us the same vector. The magnitude of this vector is going to be given with this formula. Now, what does that formula remind you of?
Pythagorean.
Good, the Pythagorean theorem, okay? And that's because that's exactly where this is derived from. Alright, if we had the vector 5, 3, or 5, -3, I should say, I'll just use it as a position vector. Let's say we have the position vector OA, okay? So here's the point A. So the position vector here is going to be that vector, OA. Yes?
The vector signs over I and J,
Mm-hmm.
is that necessary?
Yeah, because those are remember these are the unit vectors. I is the vector 1, 0, and j is the vector 0, 1. Okay. You don't see it here because I know it's hard to tell, but the I and the J up here are in bold print.
Oh, yeah, I see.
So,
Oh, we talked about it.
yeah. So it's just differences in notations, but anytime you guys are writing a vector, you need to use the symbol. Remember there was the other symbol too where you had the little tilde above it. Again, I had never seen it written that way until I saw it in your book, but so evidently it's used some places, but it's not nearly as common. Alright. So here we have this, and you remember that the magnitude on a vector, the length of that drawn vector represents the magnitude. So if we're trying to find the length of this, then you can naturally see that we can make a right triangle here. The coordinates of A are going to give us the sides of that triangle, 5, and it's a -3. Although, because we're going to square it, you don't even have to include the negative in there. Alright, so you guys know the Pythagorean theorem, the square root of 25 plus 9. Okay, so we have here the square root of 34. Right. And I will tell you, don't go further and find decimal forms of these unless it comes out perfectly even. If you have the square root of 34, you know, that's 2 times 17, so you can't simplify that radical, so just leave it as the square root of 34. Alright, that will help us later on because our magnitudes are actually used in the formula to find the angle between two vectors. Okay, we use the magnitudes, we also use a dot product, which we'll talk about, I believe it's tomorrow. You know, so leave it in a radical form when you do that, okay? Now another thing that we look at when we're talking about vectors in component form is our different operations. Up to this point, we've been doing vector addition by drawing it, alright? And when we're dealing with component form of a vector, we don't need to draw it anymore, and we're going to get an actual component form of the resultant vector. Okay, so here we have two vectors, v and u, and I just used, you know, a, b, and c and d for the different components of those vectors. And we can see here, if we do u plus v, then the result of that is going to be adding the horizontal components and then adding the vertical components. Alright, so C and A are the two horizontal components, we're going to add those together. D and B are the two vertical components, we're going to add those two together. And before we look at a specific example, you'll notice here I did u plus v and then v plus u. We already talked about vector addition being commutative when we were doing the geometric form, just drawing them. But here you can see algebraically. Notice I intentionally put them in the order that they were, that they come from these vectors, alright? Vector u is c and d.
What if one is negative then? It would be different.
Yeah, we would change that. But here, now that we have the components within the vector, these are just real numbers, c and a and c. And you guys know for real numbers that addition is commutative. Okay? here you have d plus b and b plus d. Those are just real numbers, and we already know that those are commutative. Alright, so by actually writing it out this way, if you go on into further mathematics in college and you take a course in, say, linear algebra or abstract algebra, you'll do proofs like this, where you have to prove it in general. And this is how these things are proven. You have vectors that you're dealing with, and you've got to prove properties that you've used for years with real numbers, and see if those properties actually apply to vectors now. And in this case, once we write it this way, we can then say, oh, well, c plus a equals a plus c, because those are just real numbers. Now I'm back into something I already know. And you could then, say these are equivalent because of the commutative property, therefore vector addition is commutative. Alright? It wouldn't be enough just to draw it if you were doing a formal proof of the property. Okay? So there's your abstract algebra for the day. So you'll be ahead of the game a little bit if you take that in college. I will say that was the class, that was a hard class, but that was the class where I really learned how to do proofs, because we had to do them. We had to get an A in the class, no matter how well you did on the tests, you had to complete, I think it was 90 proofs over the semester correctly, 100% correct. And I think I got like 80 or something like that. I turned in about 150 of them, but I ended up with a B plus in the class, but that was tough. But I really learned how to prove things, and it's good. You learn how to really think through step by step a problem. Well, let's look more practically here at a couple of examples here. If I were doing u plus v, we're lagging a lot this morning for some reason, then I would simply take 4 plus 1 as my horizontal component, and then I would take negative 3 plus 6 as my vertical component. So the end result would be 5, 3. Okay. So, not terribly difficult, but it's just something that we need to be able to use. Because anytime we're talking about combinations of vectors, think about what we did. If you're given a magnitude and a direction, if you can break that down into its components, then doing vector addition is actually really, really easy. Okay? Think about it. If you were given, alright, so-and-so is pulling at this direction with 30 pounds of force, and this guy is pulling at this direction with 50 pounds of force, what's the result? You could get into all the trig to figure it out with the angles, or you could break those into their components and just add the components together. It'd be two different ways of approaching that sort of a problem. Now, we also talked about scalar multiplication. And this, again, is relatively simple. But scalar multiplication, we're multiplying each component by that scalar. Alright, so if vector v is just ab, and c is some real number, then we're just going to multiply a and b both by that constant c. So using the example from above, vector v, there we go. It's going really slow today. Stop. 3 times vector v, we would just multiply the 1 by 3 and the 6 by 3. Alright, so here's 3 times vector v. We would do 3 times the 1, and then we would do times, and then we would do 3 times the 6. So of course we would have the vector 3, 18. Okay? And of course you can multiply by a negative, you can multiply by a fraction, you can do any of those kinds of things. Okay? We also are able to combine these. Alright? We can combine our operations. Here's another example. We could do something like 2u minus 3v. So, in this example, what would 2u equal? Alright, good. 8, negative 6. Someone from Miss Skokin's room already collected it. Thanks. So that's 8, negative 6 for 2u. Then we're going to subtract from that 3v. So we just said 3v was 318. Okay? And you could either do it this way, or you could say, okay, it's times a negative 3, and it would be plus the vector negative 3, negative 18. Either way will work. But then your result would be 5, negative 6 minus 18 would be a negative 24. Okay? And then, of course, we can use that to find magnitudes of these combinations of vectors. All right? Take a moment here and find the magnitude of that vector.
Since it's negative, like 3, negative 3, shouldn't it be negative between
Well, that's what I was saying. You could either do it where you multiplied v by a negative 3, and then it would be addition, or, whoops, we get pointer here. I don't know what happened there.
or just minus and 3 times.
Or minus a positive 3, positive 18. Okay, I'm not sure what happened here. My computer's kind of going on the fritz this morning. There we go. Alright. So, go ahead and find the magnitude of this then. Yes. So 5 squared, remember this is derived from the Pythagorean theorem. So we have 5 squared, and we have negative 24 squared, which is a positive 576, good. And then when you add that, you get 601. Okay, so you have the square root of 601, which
24 and a half.
24.5, okay. So if that, I don't think that actually simplifies.
No.
So you could just leave it as square root of 601. Okay? And by the way, guys, this is a little thing, but obviously for me, I want you to simplify radicals and do that kind of stuff. On the IB exam, they don't care if you put things in simplest radical form. They don't care if you put radicals in the denominator. If you give them a valid expression, then they'll give you credit for it, okay? Now you can't leave this big long thing, but you know, if you've got radicals in there, if you have a pi in there, you know, unless they specifically ask for a certain form, you know, you can leave your answer unsimplified. You could even put 2/4 instead of 1/2, and they're not going to take off. Now, I would take off because academic class, but because it's such a high stakes test, they're not going to hit you for little things like that. But that's the kind of stuff that you actually can save time on. You don't need to have to think, is this simplified all the way on the IB exam? Just write it down and you're done, go on. Okay? So, little stuff like that, I mean, it may save you 10 seconds, but that's 10 seconds you can spend thinking about something else. Alright? Alright, so, those are some of the basic operations with component vectors. One last thing we mentioned yesterday, but I wanted to make sure that we talked about again just briefly here, and that is finding a vector from one point to another, okay? If you remember, we called this, alright, if we're talking about vector AB in this case, we're talking about vector AB, this would be the position vector of B relative to A. Okay? You'll see that terminology there. Okay? When they say this, they're just talking about, alright, we're starting at A and we're going to B. So it's vector AB. Remember, each of these points could be written as a position vector from the origin to A is the vector, I should put an equal sign in there. -4, 6. And the position vector from the origin to B is 5, 4. Okay? Now, the position vector of B relative to A, you see the formula here. Whatever the 2 points are, you're going to subtract the horizontal component minus of the second point minus the horizontal component of the starting point. Alright? And here the order does matter. Alright? So what I would do here is I'm going from A to B, so I would take 5 minus a -4. Okay? And that'll be the horizontal component of that vector. Then I'll do 4 minus 6. Okay? So that would be 9, -2. Alright, that would be the vector from A to B. Now, you can do this using the formula. You could do it kind of logically, because this is very similar to something else that you've done with lines. What's that? We're talking about traveling over to another point. That's actually the magnitude is the same as the distance formula essentially. slope. Okay? Where do we have to go to get from A to B? We have to go down 2, so that's a vertical component of -2, and to the right 9, so that's a horizontal component of +9.
So we don't even need to do everything from the top.
Yeah, you don't have to have this. Where it could come in handy is if you have fractions and stuff that you have a hard time doing without writing it down, or if they're very large numbers, something like that.
Or if we don't even have a graph.
Yeah, or if you don't have a graph and you have trouble visualizing it in your head. You know, that's why you should know the formula, but it is the same concept overall as slope, because you're moving from one point to the other. Where it's different than slope is, first of all, we're not going to reduce. Alright, so if it were 8 and -2, we wouldn't like reduce that like we would slope, because that would change our magnitude. We don't want to do that. And obviously the way we write our answer is different. We're not writing it as a ratio. Okay, but we can still think of it as movement. Now, just for some extra practice here, what would vector BA equal? Yeah. BA is just, it's the same magnitude but the opposite direction, right? So it's negative vector AB, so that is -9, +2. Okay? So, again, the opposite direction is the negative vector. Okay? Does anyone have any questions? Kind of touched on a number of different topics here, but that is all sections D, E, and F. Which, if this was the first time you had ever seen it, we would take more time on it, obviously, but this isn't, so we don't need to. Alright, but hopefully this will point out maybe an area that you may have forgotten, or maybe you didn't quite cover a specific aspect of it, so that's something that you need to make sure you know. Obviously, refreshing our memories on the terminology and the notation is really key. You know, making sure that you know what things are saying here. Okay, when you see this notation, you know, you recognize that as a magnitude, and then you know how to find it and all of that. Okay. Now, I did give you some practice. Again, because we're covering a number of different sections here, it's on a number of different pages. I will be posting the notes online, so if you want to just look here to find all the problems that you need to do, you can do that once I get it posted, but I'll go ahead and post the problems online, and I'm going to let you guys use the time that we have left. I don't want you just sitting there wasting it, but use the time we have left to go ahead and practice some.